So Stefan Bluegel is a professor in Aachen and Jülich. So he's coming from Germany. So he studied in Germany, and then he had experience in the US, in Japan, and then back to Europe again. So his topics are focusing on quantum materials, topological matter, spintronics, any exotic form of magnetics you can dream of, and even more. And of course, all this combined also in using like developing theory and the codes and for high performance computing application. So all this together makes this profile. And then now I will cut it short because we are already quite late. And the floor is yours, Stefan.
Yeah, thank you very much, Zeila. Thank you very much for the invitation. It's a pleasure to be here. And thank you very much to Ricardo Rejo for choosing me as a referee. This brings me to this place. I have to say I've never been here in, I mean, I've been in Utrecht before, but I've never been at the University of Utrecht before. But as I was young, at the master student level, we studied a lot the papers of Van Kampen. He was a statistical physicist and wrote very deep papers about acousticity and things like that. So from this, you know, for me, University of Twente was very deep thinking University of statistical physics. And also some professors actually from the Utrecht University became professors at the Aachen University, Upo Felderhoff or Henk van Bylen, for example. So time has passed, and the topic is towards Cryo-Spintronics. I have chosen this title not because I'm the world expert in this field. I have chosen the title not because I have the greatest results in this field. No, I have chosen the title to pay tribute to Rejo's thesis, and I find it a very cool, underdeveloped subject, and I would like to motivate the young people, you know, to study this. And, you know, you will see I have not done very much. I understand not very much, and there's many things to do. And I feel this is also a job for you to jump out of the lecture, go to the lab, or, you know, to do this in this field. That is basically my motivation. So, you can criticize later on my work because it's rather underdeveloped. The work I have done together with, I have started this work together with Philip Rüssmann. As you see later, for doing this work, we need a computational infrastructure and technology. All this was developed by Philip. I have recently working with a postdoc at Rashba, a couple of PhD students, and I have a long-term collaboration with Phoebos Mavropoulos in Athens, and with the mesoscopic physicist Jörn Trautzettel in this field. I'm getting funding from different sources. I would like in particular to mention Bavaria. My university is not in Bavaria, but Bavaria is the richest state and a super ambitious state. And Bavaria wants to build the first quantum computer in Germany, so they distribute money to people who could help them. And you will see. I'm not quite sure I helped them, but they believe that this is. And a second important funding source is ML4Q. This means matter and light for quantum computing. So where I'm coming from, this is we call it Rhineland. These are also ambitious people: Köln, Bonn, Düsseldorf, Aachen, Jülich, and we are competing against Bavaria for building the first quantum computer in Germany. Of course, we know that the Netherlands is ahead of us. In Delft, and you know, when you read the funding proposals in the Netherlands, I think you have the impression quantum computing is very, very big in this country. All right. So when I look back now in the role of spintronics, then I would say spintronics. So the topic is towards cryo-spintronics, so I should say at least something about spintronics. So when we look about spintronics, when I look back about spintronics is a fantastic field. It is in particular fantastic because it's intellectually very stimulating. You're dealing with non-equilibrium, you're dealing with the spin degrees of freedom, you're dealing with spin-orbit interaction, you're dealing with transport, with anomalous Hall effect, you know, with Barry phases, with mixed Barry phases, with torques, you know, you have orbital physics, you have spin physics. It is a fantastic field, and we could talk about hours about this. But it has, besides this intellectual stimulation in condensed matter physics, it has also some practical ramifications. And maybe the most important practical ramification is actually this giant magnetoresistance element, which finally led to the point that we can produce hard disks cheaper and cheaper. So currently we have to produce about 60 million hard disks per month. We have produced more hard disks than human people in time. And these hard disks becoming larger and larger, storing more and more things. And if you look at the evolution of the hard disk price per terabyte, you see you are coming to a level where you can buy a terabyte maybe for $20 or 20 euros or 25 euros. And that is the reason why our children download everything. And if the hard disk is full, you buy a new one instead of erasing things. And that is the level we are. And this is actually the basic reason why we have actually this change of strategy, in the sense that we have actually cloud computing and these very big data centers. Because most of the hard disks go not to the consumer, it goes to these huge data centers, which offer services. And with the advent of AI, on this training of the large language models, the number of these big data centers is increasing worldwide. And with the usage of this AI and the usage of the data center, also the energy costs, the energy consumption increases. This is about the estimate in 2030, and it's about probably the use of electric power of Japan in 1 year, something like this. And there's of course a second aspect. You have to feed data into this data center, and this data, of course, are training, and for this you have computing sources, and basically the only thing which you have to worry about is the tier 0 computing, because all that you do with tier 0 computing today, you do with tier 1 computing tomorrow. So when you see here, you have here, oh, sorry, the colors are not visible here. So what you basically see here is a straight line. This means basically exponential growth of the demand of computing power in the world. And it here doubling every 24 months. But with the request of AI and the development of the GPUs, basically the request in the doubling of the CPU time, it changes basically to 3 to 4 months, every 3 to 4 months. And the estimates of computing power, I mean, the demand of electrical energy is about 3 to 3.5 terawatt hours. This is a number we cannot imagine, but therefore I scaled all this in Japan. This is probably 3 times the demand of Japan a year. And you know, exponential growth on a finite Earth is probably not sustainable, and therefore we have to think about other things. And the things we have to think about is, in general, is the future of computing. And you have to think more than me, because your futures last longer than mine. So basically, we discuss currently 2 paths beyond this classical computing. One is the neuromorphic computing, and one is the quantum computing. And the neuromorphic computing probably has its strength in advanced pattern recognition, in data mining, things like that. And quantum computing probably has its strengths in simulating quantum matter, and maybe in the horizon somewhere there is also what you call hybridization of large number, many things in between. So these require basically novel concepts, and actually novel materials, novel interfaces, novel systems to deal with these questions. Actually, what we want to do is in silico computing, in materials computing. What we are currently doing is we are doing CMOS, and in the CMOS we develop very intelligent algorithms on a very deep level, which is, for example, simulating the icing computer, which we could do actually in materials. But this we gain also a factor of 4 or 5 or even 10 in energy. But I think it is so basically what this strategy tells you is that you can gain enormous amount of energy, say, by writing software. If you look at the clock speed, if you look at the clock speed of a computer, it's basically stable, doesn't change anymore. And by writing the best possible software on a certain level is an option to gain energy, to save energy. But I think you cannot beat that by in silico computing, either in the area of quantum computing or the area of neuromorphic computing. So with this event of this quantum computing, of course, a lot of energy, money is involved building up these labs, these practical labs for quantum computing. That means you have to learn how to build effectively fridges. You have to learn how to wire these fridges, and you have to learn how to operate qubits at very, very low temperature in very complicated devices. And with this theme, fridges, cooling, the number of reactors involved in this cryo technology is increasing. And I think what is not only benefiting from this is not only the quantum computing, but I would say the entire cryophysics world. And with this, I'm believing that also as a spin-off of this, cryocomputing or Cryo-Spintronics will have a great potential. So as I was young, he wrote papers on surface science. We basically always want to revolutionize the catalytic reactions. It's never happened. But what's out of this developed actually nanoscience. And in a similar way, I feel that with this spearheading the quantum computing, at the end, as a spin-off, we will do something totally different. But this might be the area of quantum computing, cryo-computing, cryo-spintronics on a larger scale. All right. So the question I have is, currently, if you have a typical supercomputer, I mean, talking about Nexa scale computer, like a Frontiers or the Fugaku or the Jupiter at Jülich, so typically they request about 20 to 50 megawatt on electricity. So for example, if you go to the Fugaku computer, next to the Fugaku computer, there is a gas turbine, there's a gas station, a gas electricity station, and they produce the electricity for this Fugaku supercomputer. And then 25 to 40% of this energy goes at the end to the cooling. But the cooling water is heating a huge plant area, and you can grow very exotic fruits close to this Fugaku supercomputer. So cooling, what you do is basically the cooling is at ambient temperature, so 20 to 30 degrees, often then warm water moves. And the question I have is it not more efficient to cool this machine and take off the heat of this big machine, or building a machine at 4 Kelvin, which is much smaller, much more efficient, but then you have to cool, not to room temperature, but to 4 Kelvin. And the question is, where is actually the spin-off? And for this, so basically, of course, I'm not the first person who's thought about this. There is an important paper of 2017 by IBM, and they investigated the various cryogenic computing concepts. And you know, you have, for example, superconducting logics. You have cryo-CMOS. So if you have a superconducting logics, you need, of course, also things which operate these logics. For this, in the CMOS, you need cryo-CMOS. Cryo-CMOS need, of course, completely different, significantly different doping profile because you work at different temperatures. Or you want to have a bit quantum computers, temperatures, of course, lower. And, you know, so the great thing about these cryogenic computing concepts is that they have very, very low power dissipation and per logic operation. But I should also not ignore the energy cost of cooling. So how large is the energy cost of cooling? The energy cost of cooling, that is basically the cost you have to pay for refrigeration. And this cost is that your refrigerator and your freezer in your household is one of the biggest sources of your electricity bill. Most people do not realize this. And there's a coefficient of performance, which is basically a theoretical value, which is given by the Carnot process. We cannot do more. We cannot do better. And so if you want to cool down at 4 Kelvin and you from room temperature, then this coefficient of performance is basically 1%. So in other words, it means if you invest 1 watt, if you want to cool your system by 1 watt, you have to expend, you have to expend at least 74 watt of work. And of course, nobody works at the Carnot level or Carnot efficiency. So basically, if you have realistic cryo coolers, maybe they have efficiency of 20 to 30%. Then you need about for 1 watt of heat transfer at 4 Kelvin, you need to do 300 watts of work. And so if you compare that now with this coefficient of performance for liquid water cooling in a data center, to remove 1 watt of heat at 30 Celsius, you need about 0.2 watt. So that means you have to be a 50. So that means if you develop a cryo-electronics, your mode of operation, your dissipation level has to be 1,500 times smaller than the dissipation level of a CMOS operation. That is a huge challenge. But on the other hand, if you look at the current superconduction logic, which is in the order of 10 to the 4 to 10 to the 6 of the energy per operation of a CMOS, so in principle, it could be possible. But I have 3 ifs, because possible needs also technology. I have not the famous idea about technology myself. And when it comes to technology, you need packaging, you need data transfer, all these kind of things. But I would say it is not hopeless. I would say there is room for doing this. And of course, in principle, I'm coming from physics. So in principle, I love effects, properties, effects, electrons, doing something, phonons doing something also. But I feel at least I feel that my community, the has not reached yet the level they could have reached so far in exploring this field of cryo-spintronics. And I have not done this before. So when we think about the superconducting spintronics, irrespective whether you think about Majorana 0 modes for topological quantum computing, or you think about proximity effects to get out of singlet pairing, triplet pairing, or if you think about combining magnetism and superconductivity, something which in my lectures, undergraduate lectures, was always forbidden. Or you think about, just some diode effects, you always deal somehow with interfaces. And so, understanding these interfaces. I mean, I'm not a superconducting person per se, but of course, in order to do that, I studied superconductivity recently, but some years ago. And I was relatively surprised how long this, the superconducting BCS community stayed actually on a S-level model. So basically, everything, many things, many thoughts are basically S-level thoughts, single-band thoughts, discussions, models, and the reality. When you think about interfaces, you don't think anymore about bulk properties. The world can be different and much richer. And actually, what I want to say is this is a very rich field lying in front of us which we have not put in for. And okay, so basically, when we think about interfaces, you have to think about reality. So maybe you want to grow. Some of us are interested in thinking about topological superconductors, like you think about topological insulators. So you might combine a topological, combine a superconducting interface with a topological insulator. If you do that, sometimes you, depending on the growth, you get surprises that somehow this bismuth and this vanadium forms mixtures and has at the interface a completely different concentration. And therefore, I feel you have to study also the material science aspect of this Cryo-Spintronics technology. And to get a handle on this is that we try to extend the density function theory towards the density function theory as a practical theory for quantitative description of materials to superconductivity. And when you study materials, it is not enough to study a single material. If we want to scan a property range, so we want to do high performance computing, high throughput calculations. We want to include the superconductivity. We have to deal with real interfaces. These real interfaces are not perfect. So they have, this is also true for the interface of the transfer qubit. You have a Josephson junction, you have variations in this Josephson junction, and these variations in the Josephson junction can be Kuba pair, can lead to decoherence of the Kuba pairs. So therefore we try to have methods which we can study also impurities and defects. And all this we want to combine with the first principles electronic structure calculation of doing this first, so say, model-free first principles calculation. All right, so the first step is to think about how to treat the superconductivity in density function theory. And by this, I think the one successful path is to combine the Kohn-Sham theory with the Bogoliubov-de Gennes, or translate the Bogoliubov-de Gennes approach into the language of Kohn-Sham theory. So in Kohn-Sham theory, you work with a density. So the only thing you know is the density. So you write down your density function theory with this density, and therefore you should also get a superconducting phase. But in general, this will not happen because you do not know the function. And this is already true for magnetism. So if you do a density function theory calculation, your system will not become automatically magnetic. And if you look at the density of a non-magnetic calculation and the density of a magnetic calculation, you would not be able to see the difference. And therefore, there is also no functional which has the sensitivity to get out of these nearly indistinguishable densities the magnetism. So basically what we do is we extend the density function theory by an order parameter, order parameter density. And this is for us the magnetization density. And this magnetization density we couple to an external field. This, for example, this is the field. In ordinary density function theory, it is the density of the electrons, which is the order parameter, which you couple to an external potential. And in this way, we generalize the density function theory. We know exactly we don't have this superfunctional, which knows everything. Instead, it is easier to arrange functionals if we introduce order parameters into this theory. And the order parameter, for example, the order parameter of the superconductivity is the anomalous density, which couples then to the gap function of the superconductors. And what I would like to point out is that this order parameter is a non-local quantity. And of course, we also take into consideration the dynamics of the ions. Yeah, the dynamic, it's the kinetic energy of the electrons, the kinetic energy of the ions. We have the interaction of the ions, and we include here the entropy. And basically, you can find a very nice article by Sana written in this one. And the variational minimization of this function with respect to density, the anomalous density, the phonon vibration, you basically can derive now equations of motions, and these are typically our Kohn-Sham equation. In this particular case, the Kohn-Sham Bogoliubov-de Gennes method. So basically, you have this is the ordinary Kohn-Sham Hamiltonian. It looks simple, but typically it includes already spin-orbit interaction. Sometimes it includes magnetism. This would be, for example, here maybe a spin-up Hamiltonian. This would be here. This reflects here the holes, the electrons, the holes. This would be then hole down. You have the off-directional elements which couple the electrons to the holes, and the gap function, which might be a spin up and spin down, has spin up and spin down coefficients. And then you see basically the variation with respect to the density gives you the effective potential. The variation with respect to the magnetization density gives you the effective field, and the variation of the exchange correlation potential with respect to the anomalous density gives you basically superconducting gap function. Now, I have to say, all this is very nice, but we have no good understanding of this functional. Here we have series of approximations. So basically, what we first do, before I emphasize that actually our anomalous density is non-local. The first thing we do is we make it local. That is easier to work with. And then, in principle, this coupling constant is actually not a constant. It's actually something orbital dependent. For every orbital, you have a different constant. And also, when you work with interfaces, you cannot expect that at each atom, this coupling constant is the same. So basically, what we do is we taking approximations for this. So for those who are expert in density function theory, it is a little bit like an LDA plus U calculation. You have this Coulomb view, you know exactly that it exists. You can sometimes take it from spectroscopic data. Sometimes you do constrained RPA. Sometimes you do local density approximation. Somehow you have to get this U. And sometimes, often what we do is, we do a calculation as function of this U, and then compare our output result to experimental data. And that's basically what we also do. For example, before I want to study an interface of something, of a superconductor, I first calculate the bulk superconductor as function of these parameters and see how the gap, which the superconducting gap, which emerges here, fits to the superconducting gap measured in the experiment. Then I take this lambda and fix it. And that's the way I'm currently I'm operating them. Maybe a more intelligent way would be that you do first calculate the electron-phonon interaction, which we heard in the previous talk. Then you go to the Rashba equation. Out of the Rashba equation, you get the gap function, which is then k-dependent, k-prime dependent, and things like that. And you take now this Rashba function, the gap of the Rashba function, to determine this. Like this we haven't done yet. Okay, so now we have established the Bogoliubov-de Gennes equation. Now we have to solve this Bogoliubov-de Gennes equation in some electronic structure method. You can choose the method of choice. We have chosen for the reasons which I mentioned, because we're thinking in terms of magnetic impurities, magnetic chains on the superconductor. We are thinking about amorphous and disordered interfaces in transmon qubits. We are thinking about quantum anomalous Hall systems connected to a superconductor. These interfaces are not perfect, and therefore we have, for us, chosen the work which is Korringa-Kohn-Rostoker, Greenfunction, and many other methods are also possible. And the thesis of Ricardo Reho, he uses Siesta for that. So the key thing in this Korringa-Kohn-Rostoker method is actually the existence of a Greenfunction. And this Greenfunction, so it's not a wave function-based method, it's a Greenfunction-based method. The advantage of a Greenfunction-based method is that it contains all kinds of boundary conditions. And you get all the quantities which we need, you get basically out of this Greenfunction. For example, by an energy integration, some tracings, multiplying some operators. In particular one, which we always have to get out, is the density, the magnetization density, the anomalous Hall density, all this you get out of this Greenfunction. And this, in this method, we have basically a tessellation of the unit cell around each atom. And basically, we expand everything in spherical harmonics, charge density potentials, anomalous densities, and so on. And the way we construct this KKR Greenfunction, it is from scattering theory. And since it is from scattering theory, it has the right boundaries for transport. So therefore, we often use it also for transport together with Boltzmann and so on. And a second great advantage of this Greenfunction method is the existence of the Dyson equation, because you can always relate the Greenfunction of something complicated to the Greenfunction of something easy, which you can calculate by an easy way. So, for example, imagine you want to study an impurity on the superconductor. Then you first mentally you study first the superconductor, first the byte superconductor. That is the easiest Greenfunction. Then the next one is the Greenfunction of the surface. If you have done that, then you study the Greenfunction of the impurity on the surface. All this by building up the Dyson, going step by step with the Dyson equation. But if you include an impurity, you have to decide, yeah, what is the range this impurity may perturb the environment. And this will be is this blue thing, which I call cluster. And now we calculate basically this cluster perfect, this impurity plus the cluster perfectly embedded into the surface in this Greenfunction method. And by this, so to say, I get all the properties of the most complicated systems I can imagine by this Dyson. And then the Greenfunction reflects, of course, the structure of the Bogoliubov-de Gennes equation. So of the Greenfunction of the electrons, the Greenfunction of the holes, the Greenfunction of the electrons and the holes. And so to say, the density is given by the electrons, Greenfunction of the electrons, the occupied Greenfunction of the electrons, and some of the unoccupied ones of the holes. You get correspondingly the magnetization density by the Greenfunction of the electrons and holes times the spin density for the operators, and you get the anomalous density by the Greenfunction of the electrons. And this system basically you have to convert self-consistently. You have to go, you have calculate these quantities. Basically, this changes your Greenfunction and so on. Okay, with this, I stop here, and maybe I would like to present a few results. How do we do time actually?
Well, we're just before 5. You started a bit late, but I think
I started at 20 past.
Yeah.
Okay.
Maybe.
Maybe 10 minutes, huh? Okay. We should also not spend too much time, otherwise we cannot drink. That's also not good. So, yeah, I show you something very simple. And I think I would like to make you aware of the energy states. So this is the density of states of niobium. It is a typical density of states of a BCC material. This is the Fermi energy. All states are occupied, all states are unoccupied. So the typical bandwidth is in the order of a few EVs. That's typically scaled bandwidth. Now, if you go one step further, the spin-orbit interaction, here I choose as example the Rashba states of the gold surface. You know, might be in the order of 100 millieV, and that's already large, you know, maybe 50 millieV, 100 millieV. This is the typical scale of gold, so the heavy element, and it's a very prominent surface state. Everything is cool here. So maybe in reality might be a little bit smaller. But if you look now at the superconducting gap, the superconducting gap is in the order of 1 millieV, 2 millieV, 3 millieV. But this is another order of magnitude smaller. And so to say, the decrease of this energy scale means inversely proportionally the numerical effort which you have to take to deal with all these energy scales simultaneously. So that means the effort here, for example, a number of K points, which you have to take to integrate all these quantities, is quite demanding, for example. And a lot of attention is to be paid to this. So this is basically an extreme accuracy. And here I show, as this is also in the thesis of Ricardo. So this is the gap function, basically, of the superconductor niobium. And you see, you work here, yeah, you see there is an internal structure in this gap. It's not clear what it is, but I mean, it's clear for us where it comes. This comes from the crystal field and from certain band structure effects. And this is the scanning tunneling spectroscopy experiment. And so this is taken at 1.3 Kelvin by a group of Bode in Würzburg, and they fitted data to it. And so, of course, there is some agreement. There is some agreement. The question is, of course, in this original calculation, no spin orbit interaction was included. The question is, what's actually the role of the spin orbit interaction? And you see here the role of the spin orbit interaction in the band structure on the scale of AD. But if you look at the density of states, first of all, you don't see much changes between calculating with and without spin orbit interaction. In particular, the density of states at the Fermi energy does not change. And since the density of state at the Fermi energy does not change, it has practically, we couldn't see any impact on the superconducting gap. I forgot one transparency. Yeah, okay, so I probably took them out. So I should say that the calculation here is a bias calculation. When we take a surface calculation, so we take 21 layers of niobium and look at the surface, this feature we did not see. This is a surface science experiment. So that sounds consistent. On the other hand, if we increase the temperature at 1.7 Kelvin, I think we did 1.7, then this feature is also nearly disappeared. So I think we need, in my opinion, we need hardcore experiments now to see what's going on. So I asked the community to do experiments for niobium bulk to measure the gap function more accurately, but it seems also very experimental. It's not so easy to measure gap function in bulk crystals.
We ask a question.
Yeah.
The temperature in the simulation is the electronic temperature. It's not the real physical temperature.
It's the electronic temperature. Yeah.
And then in the experiment is the physical one.
Yeah.
That's also
different. Yeah. Yeah. But if you go, I think higher. Sorry. Sorry. One experiment is missing. I realized. So when we change here the temperature, you see that I think the 1.3 or 1.7, I forgot. This peak is also washed out already. Mm-hmm. So we're talking here about of many, but also something here, but on this level, this is micro EV, so this, I'm not quite sure, I'm confident to discuss this, but what it was for me, it was nice to see that in a completely independent method, completely independent calculation, totally not connected method-wise, and also, that independent of this, you find it. Whereas experimentalists have not seen it, and surface science is difficult, but I think we should motivate experimentalists to do this a little bit better. Okay, this I showed. So now let's come to a second subject. How do we do now? What is that?
Well, I mean, it's fine now. So
yeah. So let me think. Let me see. Okay. I have a few more slides. I cannot show them all, it's clear. Let me see how I'm proceeding. Maybe I do not show you result B. Maybe I should show you. I mentioned only result C. And the result C is a very, very funny study. I want to make my life simple. I want to study simple things. So I thought myself the most simplest interface is actually gold aluminum. Gold and aluminum are both FCC, have basically the same lattice constant, largely SP materials, but the S and P is different. Aluminum has a very strong P character, and gold has a little bit P on the surface. So gold has, on the surface, gold has a last Rashba effect, whereas aluminum has no spin orbit reaction. But aluminum has superconductivity. So I wanted to see what is this Rashba effect on the surface of gold doing to the superconductivity of aluminum in the substrate. That was my motivation. So I started a very simple thing. So basically, I have here 6 layers of aluminum, 6 layers of gold. The gold, so the aluminum has basically S and P electrons. It goes into it couples to the gold. The gold electrons come to the surface. They experience the Rashba effect, and this entire thing interferes. The way we operate is to do calculations. To understand calculations, we sometimes need models. Otherwise, it's very difficult to understand the physics. So basically, this is a typical band structure of the aluminum bands on gold, 6 plus 6 layers. And out of the entire spaghetti, I'm only interested in this very small number of states. And this small number of states you see now here, and these are these gold Rashba states. So you see the Rashba splitting of spin up and spin down electrons. And you see these are the aluminum states, and you have also picked up a little bit Rashba, but not so much. And now you can ask yourself whether I'm right or wrong. So we take a particular K point, this one, and look now at this particular eigenvalue, look at the eigenvectors and ask ourselves, where is the electron distributed? And then you see, basically, if you are at state 1 and 2, you basically see they are on top of each other. These are basically the surface states. So basically, we can understand these are Rashba active, they're sitting at the surface. And you see, these are the aluminum states, and they are basically in the aluminum. But now, you see also, if they move on and on and on, and suddenly the color here changes from blue, and here the blue goes on the other side. So basically here you have something which is the avoidance hybridization. So basically here you mix into the silver states, into the gold states, you mix aluminum states and vice versa. So therefore we look now at this K point, and then you see a different picture. You see suddenly that these state 1 and 3 have a very, so 1 and 3 is this one, have a very high amplitude on the surface. And all of them have an amplitude at the surface, but at a different level. So you see that aluminum states have mixed with gold states. Now the next thing is, now we are switching on our superconductivity. So what you see here in the superconductivity, which we switch on, is this in gray is the whole states. So conceptually, you can think that the whole states, the superconducting state, the whole state and the electron state couple, and the open band gap. Here you see this is the typical aluminum band. Aluminum is green here. You see the aluminum band opens a gap. This is the superconducting gap, and this is the gold state. But also something happens to the gold state. What actually happens is, on different levels, the s electrons of the aluminum, which have the superconducting, brings the superconducting states into the gold, but gold has a huge spin orbit interaction, and therefore you have an orbital depending on the orbital. You have different levels of singlet and triplet superconductivity. And I would like to point out, you see here this gap opening, and the gap opening, what we observe is larger for smaller K points and becomes smaller for larger K points. And you see also you have a gap opening here at relatively far energies already from the Fermi surface. So this is basically the gap opening at the Fermi surface, but you have also gap opening in the far away from the Fermi surface. And you have some crossing here where there is no opening again. This is a consequence of the inner degree of there's an inner symmetry, the pseudospin. And if they have the same pseudospin, if you conserve the pseudospin, then we have no we have crossings without a gap opening. We have 6 of these crossings and 2 I showed you. All right. Maybe this is the main message of this. Maybe we can make a model. I don't want to show the model anymore, but I want to show that our gap function has a singlet and triplet component, and the triplet component can be, depending on the K point and band, can be relatively large. This I stop and I say, what is the outlook? What I would like to study is basically a skyrmion on a topological insulator and see a skyrmion on a superconductor to see whether we can have Majorana states in skyrmions. And I would like to say that, this is a very, very rich field. We can work with a very diverse number of materials. We can go beyond this S-wave physics and do unconventional pairings, spin-off induction triplet. And for me personally, it's helpful to connect to the mesoscopic transport community who have a strong history and strong understanding in this transport phenomenon. It is. I would like to stop and thank you very much for your attention.
Are there any very pressing questions for Stefan? Ricardo and Martin?
Yeah, so thank you for your talk. It was really nice and inspiring for research that can be done on this field. I have lots of questions, but one that I would like to ask now is related to your statement about a way of improving the extraction of the lambda by doing electron form happening calculations plus non-mixed equations or with the lifetime theory. And I was wondering if we were to do so, which I think is the mindful line not so for us, would you not miss the unconventional superconductivity, or do you think you would still capture it? So how do you deal then with capturing unconventional superconductivity?
So basically, my thinking is currently focusing on BCS type of superconductivity, if you think about this. If you think about superconductivity due to spin fluctuation theory, this is a different story. Yes, my feeling is, my personal feeling is, you have to go beyond parquet. So you have to do vertex, very complicated vertex corrections. Yes, to deal with that. And I feel this is very complicated. It's not only people do that on a model level, on a two-band level.
Yeah, so this was actually my second question. To do also weak theory to count vertex corrections in the electron hole or electron. I'll ask you also.
So my feeling is, you need probably, in Higgins' equation, there is one vertex, a very bad one, which is this one. A feeling you need such a vertex to describe this superconducting thing, and that is not so easy. Or you have to have maybe a parquet where you have connected to some of the electron hole pairs, maybe some renormalization flow, which gives you enough strength for the Cooper pairing. But I'm not an expert in this, and I'm a colleague of mine in Köln is working on this, but only on the two-band. That is very complicated, numerically very complex. I wish to do that in somehow an extension of extension of GW or GW plus T or something like this, but I'm not competent enough to do that. And I think it's also numerically very, very difficult. You have the number of momenta, maybe 12-dimensional dimension space, momentum space.
That's all.
Until your last slide, I was going to ask you the following question, which I'll ask anyway. You seem to be taking money from the guys who do quantum computing, but your title is Cryo-Spintronics, which feels like you're going to do classical spintronics, but in a cryo setting. So you've motivated both, and with your last slide, you can sell it to them as well. Do you think there's more promise on one side rather than in proper quantum computing, or we don't have to wait for them to fix the quantum computers before we can do something useful with this?
The word propagates non-linearly. Nobody knows exactly how we move on. But there's a lot of effort in quantum computing, and I'm sure the quantum computing guys will make some progress, and we will solve quantum models with quantum computing for sure. But on this way, there are also other low-hanging fruits, maybe which are also very interesting and very inspiring, and also have consequences for our technology. Yeah.
I think with this wise words, I will thank Stefan and Bluegel again, and invite you to the board and stage.